Alrighty, here we go. This is going to be a recap of the volumes of Solids of Revolution that we've covered thus far. I'm just going to basically, at this point, because we've already talked about the concepts behind them, I'm just going to write down the formulas for the disk and shell method. And then we're going to just start doing some problems and start applying these methods. So let's get started. So, as we said before, if you're trying to find a volume of solid revolution using the disk method, the volume using disk is going to be pi times the integral of the radius, and I'm putting radius for a specific reason and not putting an actual function because sometimes it varies. Okay, so I'm going to put radius here, so pi r squared, so that's the radius square. Okay, and then it's going to be your variable of integration. Okay, and I'll just put that in parentheses. I'll say variable of integration, and what I mean is dx or dy. Okay, that is what we called before the thickness. Okay, so you can also think of this as the thickness of the slices. Okay, so that's that. We also have the shell method. Okay, and for shell, so we have volume, okay, and we want shell. For this one, we're going to have 2 pi times the integral. And also, I should have put bounds on this, so I'll put from A to B. I'm sorry about that, my badness. Here as well is going to have limits of integration from A to B. And here, we're going to have 2 pi times the radius times the height times the variable of integration. And the variable of integration, in the same way that we had for the disk method, this is going to represent the thickness. Okay, so those are our formulas. Now, one of the examples that I went through before was finding the volume for the function x squared from 0 to 2 rotated around the x-axis. And in the session, I couldn't figure out what the error was. So now I'm going to correct that. Okay, so here, let's take the example f of x equals x squared. Okay, and the interval that we did this on was an interval from 0 to 2. Okay, and here we're going to be rotating this around the x-axis. Okay, so let's draw this first. So if we draw this, we get an image like this. Okay, and this is our x squared function. Now let's say that this point here is 2. Okay, so this inside thing is my region. Okay, all of this stuff here is my region. Okay, and the first thing that we said we're always going to do when solving these problems, okay, is to first choose the type of rectangle you're going to have. So that is, first choose whether you're going to do horizontal or vertical rectangle. So let's choose the vertical rectangle first. So the first thing we're doing is choosing rectangle. So we chose the rectangle Okay, and in this case we're doing the vertical. Okay, so let's draw that in. So the vertical rectangle would look like this. Okay, and you can fill that in as you'd like so. Okay, and now that you have your rectangle, now you have to actually do some visualization. So again, we're revolving this around the x-axis. So think about it like this. Okay, take your pencil. Okay, so this is what you do. Place your hand in a horizontal fashion and place your pencil in a vertical fashion. Okay, and then rotate your pencil around your hand and see what type of shape you get. Well, if you do that, what you'll find is that you'll get a disc. Okay, so you'll get a disc or a circle. Okay, hence the name we use disc. So you get a disc or a wheel or whatever, what have you. So that's going to tell us what method that we're doing. So once we choose the rectangle and then we visualize, that will tell us, well, what type of method we're going to use. So here we're going to use the disc method. Okay, so we know we're going to use the disc method, so let's actually write down the formula. Okay, so the formula we said for disc was that volume equals pi times the integral from a to b of the radius square times the variable of integration. Okay, so now we have our formula written. In this case, remember that the variable of integration represented the thickness. Okay, so if you go back and look at the figure, the thickness of these slices or these cross sections that we're taking, the thickness is going to be the base of that rectangle. If you think about it, if you're rotating your pencil around the axis, the thickness of that pencil, okay, is going to be this horizontal distance, which is a change in x, which we denote dx. Okay, so our variable of integration in this case is dx. Okay, so here we can just transform this from pi times the integral. Okay, and here we're going to have dx. Okay, now the second thing is identifying the radius. Now think about this again. Your pencil is rotating around the axis. So you're creating a circle or a disc, as we said. But think about it like this. The distance from the axis to the function would be your radius. Okay? From the distance from the axis to the top of your pencil is the radius, and then the distance from the axis to the negative orientation of your pencil would be the other part of the radius. So we would have it's like think of your pencil as the radius of the figure. Okay, so the radius here would be from the function y equals 0 to the function y equals x squared. So our radius is going to look like this, and I'm going to write it like this purposefully. Okay, so here we have f of x squared. Okay. And now we know what the radius is. The radius is the actual function, okay? And we know the variable of integration is x, so that means we're integrating over some x values. In this case, our x values are ranging from 0 to 2. So those are going to be our limits of integration, 0 to 2. Okay? And now if we rewrite this, we get the integral from 0 to 2, and of course pi in front. And then f of x is x squared. So we have x squared squared, which will be x to the 4th dx. And that's going to be our integral. And once we evaluate for this integral, we're going to have a solution for the volume. Okay? So, now let's go ahead and actually solve for this integral. Okay? So, we get pi. The integral of x to the 4th is x to the 5th over 5. So we get pi over 5 times x to the 5th. And then we're evaluating from 0 to 2. And if we do this, we get 2 to the 5th minus 2 to the 0, which is just 2 to the 5th. So that's 2 to the 5th times pi over 5. Okay, so we get 32 pi over 5. And that is our volume. Okay, that is the volume of the solid that we get if we rotate this figure around the x-axis. Okay? And so this is our volume. Okay? Now that's the disk method. But how did we form the disk method? Well, it depended on our choice of rectangle. We chose the vertical rectangle. So now what happens if we choose the horizontal rectangle? Well, let's see. So let's do number 2. This is method 2. Okay. So here we're going to choose horizontal rectangles. Okay. And let me draw the region again so that we can kind of look and analyze this. Okay, so this is what our function looks like. Okay, and we said, okay, this is 0 to 2. Okay, and what we're going to do is choose the horizontal rectangle. So in this way, we're going to choose a rectangle that looks like this. Okay, and then you can shade that in as you like. And remember, again, we're going around the x-axis. Now, the same way that we did for the other problem, well, the same problem, but the first method, what we did was we said, okay, place your hand horizontally, okay, because that's representing the axis, and then take your pencil, okay, in this case in a horizontal fashion as well, and take your pencil and go around your hand. Okay, and if you do that, you should see that you get kind of a canned shape. Okay, so a canned shape, okay, and in mathematics we call that a cylinder, and in the case of these volumes, we call it a shell. Okay, so we get a shell, so we're going to use the shell method. So let's write down our formula for shell. Well, volume, according to shell, is going to be 2 pi times the integral from a to b of the radius times the height times the variable of integration, which we also know is our thickness. Okay? And the easiest thing in these cases is to identify the variable of integration. So we'll do that first. Well, here you see the rectangle is horizontal, but the base of the rectangle is no longer on the x-axis. Okay, it no longer represents a delta x, rather it represents a delta y. That is, we have a change in y, so our base here is dy. So that is our variable of integration. Okay, so we're going to just rewrite this as 2 pi times the integral from a to b of the radius times the height times dy. Okay, now the next thing we need to do is identify, well, what is the radius and the height? Okay, so in this case, we have a variable of integration dy. That is, in order for me to integrate, I have to have an integrand that is a function of y. That is, the radius times the height must be a function of y. Because that's the only way that I can integrate. Okay, the only way you've learned to integrate single variable functions is given the variable of integration that you're dealing with. Okay, so we need things in terms of y. Okay, now if we look at this, okay, we can think of, if you think about rotating this pencil horizontally around the axis, like we said, we get a shell. Okay, but if you think about it, the radius, okay, of your shell or your cylinder, okay, the radius of that would be from, and then look at the diagram, the radius would be from the x-axis to the function. The x-axis to the function. And notice the way I'm drawing this, that the distance from the x-axis to the function is not always the same. That is, it's varying. So we need some way to deal with that. Okay. So the question is, well, how do we deal with that? Okay. Well, since these heights are varying from 0 to the function, we know that these heights are going from the axis to x squared. Okay, remember that this is y equals x squared. Okay, it's going from the axis to the x squared function. Okay, well, the x squared function is really y. Y equals x squared. So, what we have here for the radius is y minus 0. Okay, y minus 0. Okay, so what we have here is 2 pi times the integral from a to b. I'm not going to write a and b right now. And then our radius, like we said, is y minus 0. Okay, so we have our radius. Now we need our height. Okay, so our radius was going in this direction. If you think about your pencil again, rotating around the axis, the length of that pencil is going to be your height. Okay, and the height, if you look back at the diagram as I'm drawing this, the height goes in the perpendicular direction to these radii. Okay, and notice where these horizontal segments go. These horizontal segments go from this function to x equals 2. So if you think about this line, the edge of this region as x equals 2, okay, they go from x equals 2 to the function. Okay, now recall, we are we are integrating with respect to y. So if we're integrating with respect to y, our functions must be in terms of y. Okay? So y is now our independent variable. And now x is our dependent variable. So we have to rewrite this function as x equals g of y. Okay? And well, in this case, we can easily solve for x, okay, because y equals x squared, x would in turn be the square root of y. So x equals the square root of y. Okay? So our height in this case is going to be 2 minus the square root of y. And why am I saying 2 minus the square root of y instead of square root of y minus 2? Well, because if you think about y as being the independent variable, okay, that means you can turn your paper sideways and see that if you have y being your independent variable now, because we're switching the x and y axis, if you have y being your independent variable now, then your top function will be 2 and your bottom function will be square root of y. So one way to memorize this is when you're calculating these things, it's top minus bottom, or rightmost minus leftmost. Okay, so I'll put down here as a sidebar, rightmost minus leftmost. Okay, so in this way, our height is going to be 2 minus the square root of y. And then, of course, our variable of integration is dy. Now, all we have to do is put our limits in. Now, so our x values originally went from 0 to 2. Okay, in this way, all we have to do is plug in and see what our corresponding y values are. So in this case, if we plug in 0, we get a y value of 0. Okay, so our lower bound is 0. For the upper limit, if we plug in x equals 2 into this, okay, we get y equals 4. Okay, so our limits of integration are going to be from 0 to 4. So, we now have our completed shell method for volume. Okay, now, just a comment about this. Notice that in both methods, we are rotating around the x-axis and we're rotating the same region. Okay, so we're going to get this in the end. We're going to get the same shape. So if we have the same shape, both methods should give the same volume because we have the same shape. If you should never get something that's different because the orientations are the same. So what I'm saying is both disk and shell should give the same answer. So when we integrate this, we should get the answer that we got before, which is 32 pi over 5. Okay? So let's integrate this and let's see, is that actually correct? Okay, and this is kind of a check. If we get something that is not the same, then that means we made an error. Okay, that means that you've done something wrong. Okay, so let's integrate this. Okay, so if we integrate this, we get the 2 pi. So we get 2 pi times the integral from 0 to 4 of, what is this? This is 2y minus y times the square root of y. Well, y times the square root of y is y to the 3 halves. So y to the 3 halves. Okay, and then of course our variable of integration is dy. So let's integrate this. So we get 2 pi, okay, and then the antiderivative of this is going to be y squared minus 2/5 y to the 5 halves. And then of course we're going to evaluate this from 0 to 4. Well, if we evaluate this from 0 to 4, we get this equaling 2 pi times 4 to the 4 square is 16. So 16 minus this quantity. So 4 to the 1 half is 2. 2 to the 5th is 32. 32 times 2 is 64. So we get 64 fifths. Yep, 64 fifths. Let me make sure I did that right. 4 to the 1 half is 2. 2 to the 5th is 32. 32 times 2 is 64 over 5. So we get 64 fifths. And then if you subtract 0, then those other terms go away. So we get this expression here. So let's simplify this expression. Okay, well, if we reduce this, we get 2 pi times, okay, let's do common denominator. So common denominator is 5. 5 times 16, that's 50 plus 30. 50 plus 30, that's 90. Okay, and then 64 over 5. 90 minus 64, that's going to be 6 plus, 6 plus 20, so 26. Okay, 26 over 5 times 2 pi. Okay. Let me see. I'm back now. Okay. I see. I made an arithmetic error here. 5 times 16 is not 90. 5 times 16 is 50 plus 30, which is 80. Okay, so this should be an 80 here. So we get 80 minus 64, okay, which is 16. So we get 16 over 5 times 2 pi, which is 32 pi over 5. Okay, so again, we got the same answer with both methods. Okay, so now take this information, look at the notes that we took during the session, and go through some of the problems that I'm going to send, and also some problems from the book, and then I'll see you in our next session. Bye-bye.